Hello. In this video, we're going to look at modelling assumptions. So last time I talked about how with a mathematical model we want to solve a problem, and then I said most of the time in real life we've got to solve a problem head on exactly. We need to simplify it by making assumptions, right? And then we can sort of use math to solve it, right? To well, not to solve it exactly, but to find a sort of a good solution. So it's not the exact solution, but still good enough, because of the idea of it being that if we make assumptions, we kind of simplify the problem down a bit. So it's not it's not the exact problem we want to solve, but it's a close enough problem. By making these assumptions. So making assumptions is the key idea here. So that, and particularly in mechanics, there are a few assumptions you do need to be aware of, and we will be using all throughout the course. So that's what we're going to go over now. Right, so first of all, before we jump into it, I want to just talk very briefly about the idea of dimensions. So when we say something is dimensionless or has no dimension, it's just a point, okay? It's like a coordinate, right? Then if it's in one dimension, then it's just a line, right? Then if it's in two dimensions, then it's sort of a 2D shape, so like a rectangle or something like that. And then in 3D, well, obviously you have a 3D shape like a cuboid or something like that. So we're adding dimensions on, right? So obviously there's no dimensions here, but in one dimension that's a length. And then in two dimensions we have our length, right? Our length, I'll do up here, my length, but also an additional dimension, we have a width as well, right? And then when we get to three dimensions, we have a length, we have a width here, but also it goes up, so there'll be a height as well. So we're just adding on a sort of a different dimension on each time we go, right? So no dimensions, there's no length, there's nothing there, it's just a single point. There's no length, right? Then in dimension one, it's just a line, so that just has length, the side of the line. Then in two dimensions we have length and a width, like a square or rectangle. And then in 3D we have three different sort of sizes, right? Length, width, height, and that would be, for example, cube or cuboid, right? Okay, so with that in mind, then these are the various assumptions we will be working with. It's a lot, right? It's a lot. Now, what I do not advise is just sit there and memorize it, especially at the start of the course. What I probably would do is, obviously throughout the course we will be referencing and using pretty much all of these, more some than others, but you will see all of these in action at some point, either in year one or in year two. Okay, so all of these different assumptions, which are on the left, right, and what the assumptions mean on the right, we will be using throughout the course. Now, if you're at the start of the course, I would not sit here and memorize it. You wouldn't even know what it means, right? Like if I just sat there, like even if I started it, like what does any of this mean, right? So what I would advise is maybe at the end of mechanics, either year 12, year 13, maybe look back on this and then see, I used it for this sort of example, I used it for this part of the course, that's what it means, and then it will start to connect more. But I don't know why, I think it's a bit of a poor organisation from Edexcel, to be honest, to put it here at the very start, but I'd more or less use this as a sort of reference frame, rather than just learning it all now. With that in mind, I'll try my best to sort of explain it all now and what you need to know with all of this. Try and make it understandable, even if you're just starting the course off. Okay. So I'm not going to go over the whole list. What I'm going to do instead is just go over the main examples you will see throughout the course, and then where these modelling assumptions come into place. So first of all, we have a particle, right? So I'm going to go up and then look at particle. So firstly, particle on the top. The assumptions are the mass is concentrated at a single point, and any rotational forces, so forces that cause something to move or turn or something like that, right? Like a centripetal force, something like that. Any rotational forces and air resistance can be ignored. Right. So one example we'll be looking at is to do with cars that drive and move forward. Now again, with cars, they typically, obviously if they're moving forward, they have air resistance, right? If you stick your head out inside of a window or your hand out a window, you'll feel a lot of like a big force on you. That's air resistance, right? And so typically what we do is we try when we model a car or anything as a particle, there is no air resistance or rotational forces. So that means nothing to make the car skid or something like that, or skid on or move to the other side of the road, or kind of have an imbalance. The car just moves straight forward, okay? There's no rotating, there's no turning or anything like that. So we model it as a particle to avoid those complications. And also the mass is at a single point as well. So what that means in terms of the car is in maybe the middle of the car. We're just saying, instead of like the mass being distributed throughout the car, maybe there's a lot of mass near the engine, there's less mass maybe near the top, but in reality a particle, all the mass is at a single point, okay? It may be in the middle. So the mass is 1200 kilograms, right? That's a particle. So there's no air resistance. So if the car is moving forward, there would be no air resistance or any sort of rotational forces or any sort of turning effect from a force, okay? And so that's the main one. Now, what I also want to talk about is that this car is on a straight road. And when we move along a surface, like a road, there are two types of surfaces. It could be a smooth road or smooth surface, or a rough road. Now, a smooth road has no friction, but with a rough road it has friction, okay? And you can see that here, smooth and rough surface here. So you can see here, with a smooth surface there's no friction between the surface and the object. With a rough surface there is a frictional force, okay? So smooth means no friction, rough means yes, there is friction. So it depends on the question. So the road may be smooth, so friction, again, if the car was moving forward, friction, like air resistance, would oppose the motion, right? So friction would be there, but if it's a smooth road, there's no friction. But there is, if it's a rough road, then yes, there will be, okay? So that's that. Now, I'm going to look at this now. I want to look at rods. So, rods are now a line, right? This line AB, the line AB is a rod, okay? The whole line A to B is a rod. And for example, in this context, in year 2, we will be looking at, for example, seesaws, right? So we have two people on the seesaw here. So the seesaw itself is modelled as a line. It's modelled as a rod, okay, this line here. And again, think about seesaws. Seesaws have mass. They can be quite heavy, actually. So they have mass, right? So a rod has mass, but it's concentrated along a line. That's basically saying the rod is just one line, okay? And so therefore it has no thickness. That also means basically it's just a line, right? It's not 2D or 3D or anything like that. It's literally just a line like that. It's just a line with no thickness, right? So no thickness being, if we added thickness, it will then turn into some sort of rectangle like that. But if there is no thickness, it's just literally a flat line. And it's rigid, okay? So rigid, so again, if you think about seesaw, for example, completely rigid, it's stiff, it won't bend in any way or buckle or anything like that. So it's completely stiff, completely rigid. So that's the main idea of a rod, is it's completely rigid, it won't bend anyway, and it's just a line. And what we will be considering as well is applying forces to it. So if we impose a force here, and also the people themselves will have a force, they'll have a weight that pulls them down, right? They have a weight that pulls them down. And then we might have additional forces on the rod. What happens to the seesaw as we apply forces throughout the seesaw? The seesaw will then sort of maybe then go up and down. It might turn. We will look at something called moments, where, say if we have more people, let's say if we move everyone or this person, say if they sit right next to Sophia, then actually you'd expect the seesaw to go to tilt downwards like that. Okay, if you have two people sitting on it at the end, then what we will explore is how the rod, right, this line, the seesaw AB, how it will go up and down, okay, like a seesaw. And that's to do with moments, okay. Now the other thing we'll be looking at is this little triangle here. This is called a peg. Now a peg is simply called a support, basically a support. So it's something that it rests on, very essentially. So a peg is a support, right? It's a support that something rests on. So again, like a seesaw, and it's dimensionless. So again, that means it's just basically a point. Okay, it's just a point, really. And that's really it. That's really it, really. So a peg is just something rests on, essentially, that keeps it balanced. Another type of rod is ladders. Okay, again, we'll see this in year 2. For example, ladder that's inclined on a wall from the ground. That's the real life scenario. Mathematically, it will look like this diagram here. And you'll see here, it's again this rod, this line AB is a ladder, but it's resting on a peg. Okay, does it look? It looks a weird peg, right? But you can imagine this peg is grounded right from this other thing here, from the ground 3 meters up. But the peg itself, this circle, is holding the ladder at rest. Okay. So the peg is keeping the ladder, the rod, technically still. Okay, so it doesn't slip or anything like that. And so we will be looking at that. That's rods. Okay, now lamina. So what we looked at so far is a particle. Now particle we can just draw as a point, right? As we discussed, a particle, its dimension, there's no dimension, so it's just a point. Okay, and because it's a point, the mass of the object is at that single point. So a particle is 0d, no dimension. A rod is a line, that's 1 dimension. And now a lamina is 2 dimension. So now we have a rectangle, right? Not just a line, not just a point. We only go up to 2 dimensions here, and honestly we don't look at laminas, to be completely honest, but we still need to know it. And so with a lamina, we were looking at it through the lens in year 2. In year 2 we'll be looking through the lens of, again, this idea of moments, which is basically how we can sort of, with a force, sort of turn the rectangle. So I've included this diagram here. So if we have the force here, 12 newtons, but it doesn't matter, it's just a force, right? If you imagine we hold physically this whole rectangle A, right? It's completely still. It's completely still. We hold it with like a hand very firmly at A, right? That's sort of where we press the rectangle to hold it down. If you then imagine we push a force exactly here at 12, the lamina won't rotate in any way. It won't move, rotate in any way, because if you imagine we're applying the sort of force that way to keep it still, we press to A. Imagine we have some force holding it still at A. Then if we just do the opposite the other way, it's still, what we're doing is opposing that sort of force, if you will, to not make it move anywhere. So we won't rotate. However, if we then move it to the point C, it's now, we're now kind of, it's not really the same sort of level. Like here, it's completely the same level, so it won't move. But here, what would if you imagine, if you hold it still at C, what would happen is this sort of diagram here, which is why I've included it here. Hopefully you can imagine, if we hold it still at C here, and we push it here from here, the whole shape there, it would kind of rotate anti-clockwise that way. So what would happen is we start with this rectangle here, the green rectangle. Again, this is where we're holding it here. So what would happen is if we pushed it here, if we pushed the rectangle that from that point, it would then rotate 90 degrees, and then we would end up perhaps with this sort of orange rectangle here. So this diagram hopefully sort of, it's again really hard to explain the visualization of it, and we were doing it in year 2, so do not worry if you don't get any of this really. But the idea is, if we hold it still and then we push it, it will kind of rotate like that. Okay, and you can see the rectangles, that the rotation as we move along. Okay, so if we were to push the force and hold it at C, then actually the green rectangle like we start with would then rotate that way. Okay, and we end up there. Okay, enough about laminas. And by the way, the assumptions with a lamina, mass is distributed across a flat surface. That's basically nothing. We don't deal with that. What it means across a flat surface, obviously, it's the surface here. So the mass is evenly distributed, so it's not uneven. Say, for example, we don't have a lot of mass at one end of the lamina, of the rectangle, and then just a little bit elsewhere. It's completely evenly distributed across the shape. Okay, that's what we mean by that. And so that doesn't affect how it turns or anything like that, right? Because if you imagine if the shape was lopsided, it would have a tendency to move or turn in a particular way if it was more lopsided or the mass was heavier at one side of the shape. Okay, so that's lamina. String. Okay, string is next. So what we will also be looking at is a car, right? But also a car that tows some sort of extra weight, or a caravan usually. So a string, they're connected by a string here. Okay. Now there were two assumptions coupled with strings, and that is light and inextensible. So firstly, light means no mass. So imagine a string comparative to sort of a car and a sort of extra vehicle, right? The string has no mass pretty much. So we call it light. Anything, not just a string, that is light has no mass. Okay? And what it also means for strings, if we go up, where is it? Here, light object. So object has no mass. Also with the string, the tension is the same at both ends. So with a light, so the tension is the force in a string. So the string has, so if you imagine a car that's driving forward, there's a tension that way in the string. When it's light, the tension is the same. Okay, so at both ends of the string, obviously there'll be tensions at either end as it connects to two different vehicles. Now, you might expect maybe the tension, the sort of the force within the string will vary as we go from a lighter vehicle to a heavier one. But actually, when it's light, it has no mass. The string, the tension, the force applied throughout the string is equal as well. So the tension is equal at either end of the string, so it pulls it with the same sort of force, the two vehicles together. Inextensible then means, well, the car and the vehicle, or this extra thing here, accelerates. Okay, we call it the acceleration A. Now with any again, you'd expect maybe with two different vehicles they'd accelerate differently, but when they're inextensible, the acceleration is the same. Its acceleration is the same throughout the whole string. So when it connects one part of the string, one end to another with two different vehicles, all throughout the string, the tension's the same. So that means both vehicles or both objects travel with the same acceleration, despite if they have different sizes or forces applied to them. If the string connecting them is inextensible, then the two objects it's connecting the string, them two objects have to have the same acceleration. Okay, and so okay. And with that in mind, talking about objects being connected, we'll also be looking at pulleys. Okay, now a pulley is this sort of situation here. So if you imagine something or someone pulling something or someone that's connected. So we have a string again. We have a string here throughout the pulley, and the string is connecting two things together. So here the person and the box, right? You can imagine one end of the string is pulling the other end of the string up, and that's a pulley. Okay, this idea about a pulley, string flows through it, and then it moves the two objects up and down or whatever, right? That's the idea. And again, as a diagram, mathematically, we will be looking at it like this. So this circle is the pulley, and then if you imagine a string, a string like that goes through the pulley that way, and it connects to two sort of objects P and Q at either ends. Okay. So if you can imagine, if you pull Q down, so the end Q, then P would go up. Okay, so again, if the person here keeps tugging the string downwards, it would move the box upwards. Okay, and vice versa. Okay. And so as for the pulley itself, then, right, the pulley itself, there are some assumptions about the pulley machine here. So the pulleys, at least in this course, will be smooth and light. So as we already discussed, smooth means there will be no friction, and light meaning the pulley has no mass. Okay, final sort of example is beads. Now, beads pretty much never come up either. It's one you need to know, but doesn't really come up. Now, I've included this diagram just to help you visualize what we mean by bead. It's basically kind of like a particle, right? It could be a particle, an object where it threads through a string. Okay, like this diagram here, like you would have seen when you were a kid or something like that. These little play beads, these sort of beads, right? These objects that have a hole in them where it can pass through either end of the string. Okay, that's what we mean. So if you imagine in this diagram here, this is an example of a bead. Now initially, right, let's say we have either end of the string, right, at A and C. And so what we're saying here with a bead is that the bead can literally pass through and move between the string from point A to point C, the either end of the string. It can literally pass through, it can move forwards and backwards. What that will mean is, because strings are light, usually the strings themselves have no mass, what would happen is, as the bead, again, through the ends A to C, as this bead moves through the string might droop downwards. Okay, so let's say the bead is here. Because the bead or the particle has a sort of mass that's pulling it down, right? It'll pull the string down as well. Okay, which hence we get the diagram here. So what we're going to look at is beads that move through a string. We're not having instant like this, where a bead, or basically a particle, being pulled down or moving along a string that's being sort of pushed by some forces. Okay, so that's what all we mean by string, by a bead. Okay, essentially is it's something it can move through a string, like this sort of example here. Okay, it threads through a string, so it can move across it. It might then force the string to come down like this. Okay, kind of like a slingshot. Okay, and the assumption with a bead, with a bead here. Here, so it's a particle with a hole in it, right? So it's basically a particle, and it moves throughout the string, and the tension is the same on either side of the bead. So again, this idea about tension being equal on either side of it. Again, as we discussed initially, the rope is flat with nothing on it from A to C. Then in this example, we have this particle here that's pulling the string down. But what happens is there's tension either side of the particle on the string. The tension is the same. The force in the string. Okay, either side of the particle, because again the particle moves through the string. It creates two parts of the string. Obviously, the part from A to the particle, then from the particle to the other end, the tension either side of either part of the string will be the same. That's a bead. Okay. One more thing we need to talk about before we move on. The last assumption you need to be aware of. Actually, you might see something called a wire. A wire is basically so it says it's one dimensional. It's basically a string. Okay, so if we go back to this car example, the towing example, instead of a string you might have a wire. Okay, but again that doesn't come up. Okay, really, we deal with strings like 99.9% of the time. The last thing we need to talk about is for example here. Okay, we talked about how the rod has a mass itself, right? Now, what we can also say is something can be uniform. Okay, what it means to be uniform, if something has mass along a line, say for example like a rod, when it's uniform, mass is in the middle. So again, we will be seeing this in year 2. So let's say the middle of the seesaw here from A to B. Let's say the middle's here. That's where, if the seesaw or the rod was uniform, all the mass of the rod will only be centered at that sort of midpoint. Okay, all the mass will be contained in that sort of in that the midpoint, in the middle part of the swing of the seesaw there. Okay, so I'm going to say all mass at this center point here, which means it's uniform. Okay, so here, uniform, the mass is distributed evenly, so the mass of the object is centered at a single point, which is the center of mass. So again, where all the mass is along this sort of seesaw here in the center, that is called the center of mass. Again, we'll be seeing that in year 2 with a lamina. Where's the lamina? Here, a lamina obviously will have a mass again, but again in the center it will be literally in the slap dab middle of the rectangle. Okay, the center of mass, where all the mass will be, if it's a uniform lamina, will be in the midpoint, again in the middle of the rectangle, the area here. Okay, where all the mass of the lamina is. And that's it. That is it for now. We will talk about gravity later on in the next chapter. All you need to know is that gravity, is basically where something is moving down, is always 9.8. Okay, in this course anyway. At least on Earth, when things accelerate down because of gravity, they're falling, it will always be 9.8. We'll talk more about that though, but these are all the assumptions you need to know. We just went through them all. Again, maybe save it, or maybe come back to it at the end of the course or something like that, and then hopefully you have a good idea how we applied all these assumptions. Okay, so what I've done here is went through the examples you will need to know in year 1 and year 2, but we will be seeing all these examples quite often. So again, you don't need to memorize them now if you're at the start of the course, but you will see all these in action and exactly what you need to know. Okay, these are exactly how we apply all these assumptions. Okay, right. Okay, so we've got this example here, and we're told a mass is attached to a length of a string which is fixed to the ceiling. So what we've got here is we've got a ceiling, and then we've got this string, and then a mass at the end of it. Okay, kind of like a chandelier, and the mass is drawn to one side of the string taut and allowed the string. Now taut means inextensible. Okay, that's another word for inextensible. And so it says state the effect of the following assumptions on any calculations made using the model. So again, the model, this is a model because we're making assumptions about the string being light and inextensible and the mass being a particle. So this is a particle and the string is light inextensible. Okay, so what do all of these mean? Well, we just need to sort of just say what we just went over. So if you again refer to these list of assumptions, what we went over just is a string being light means string is light means it has no mass, but also tension is the same all throughout the string. And inextensible, the inextensible part of the string, what it means, well, I talked about earlier how inextensible of a string here in this example is when two objects are connected by the same string, the accelerations are the same. Okay, in this example that's not really applicable because obviously we just have one particle, not two things connected together. So there's no really accelerations to consider that are to make them equal because it's just one thing. Well, it simply means then, inextensible means it doesn't move or stretch in any way. So it means the string does not stretch. So it's kind of like the rods of the seesaw example, where it's just completely rigid, it doesn't bend in any way. It's a similar sort of idea here with strings. So the string does not stretch in any way, it's just completely, that's it, it's just inextensible, no stretch on it or compression or anything like that. And you can see that here. Again, where was it here? Inextensible string that does not stretch under load. So when we add that particle on, that drags the so again, when you have this string and the particle pulling the string down, it's still inextensible despite the particle pulling it down. So it does not stretch under any load. What that does mean is then if we do have two particles or two objects connected together, then the acceleration is the same. Okay, because the tension is sort of the same throughout. The tension doesn't affect the acceleration, which means the acceleration can be kept the same because the string is kept the same. Okay, essentially. So that is the assumption. That in your if you do further maths, further mechanics, but you'll spend time considering strings that are not inextensible, which you'll see will make the problems a bit more complicated. But for now, it does not stretch, it doesn't extend or compress in any way. It's just that's the string and that's it. Part B then, it says the mass modelled as a particle. What does a particle mean? Well, as we just looked at, particle probably the most common assumption, the thing you will use in mechanics. You use it all the time. Particle means essentially it models the object as a single point, so it's dimensionless pretty much, which means, for example, its mass has to all act around a single point because the object itself is a single point. And also, what that means is we can ignore air resistance and rotational forces. Air resistive and rotational forces acted upon the particle. Okay. And so there we are. Those are what the assumptions mean. So the question is just getting at, explain and just recall, what do these assumptions mean? Light, inextensible, string, and a particle. Those are what they mean, which we went over. But yeah, we're talking about a fishing rod manufacturer which constructs a mathematical model to predict the behaviour of a fishing rod. The fishing rod is modelled as a light rod, so light and rod. Okay, so firstly, light. What does that mean? It has no mass, right? And it has no mass. And then the rod is, again, it's one dimensional. It's a line, right? So it's one dimensional, and that it means it does not bend. So it's one dimensional, a one-dimensional object, I should say, which is rigid, so does not bend. Okay, and you might see as well, because it's one-dimensional, you might say it has no thickness as well. Well, if it has no thickness, then it's one-dimensional. So yeah, that basically means it's not sort of rectangular like this. It's just a completely one line, a linear sort of rod. Okay, it's literally just a line, no thickness. Okay, so then that's the assumptions. And part B, comment on the validity. So how valid or sensible are these assumptions? And this is basically what modelling is. So we need to critique, determine how valid and sensible assumptions are. So firstly, light, no mass. Well, if you think about it, fishing rods are kind of light, really, especially when you might have a heavy fish on. So really, this one is quite plausible. You'd expect a fishing rod would be expected to have little mass anyway, especially when you capture a heavy fish, when it has a heavy fish on it. So it makes sense for it to be lighter. Also, then it's one-dimensional. So it's just, again, it's not like this, but it's just a literal line. So it's a line that might have a hook on it at the end or something like that, right? That makes sense. They're quite thin. So also, fishing rods are quite thin. So it's expected, so it makes sense to be one-dimensional. So a line, basically, or in other words, has no thickness. Now, the last one's quite troublesome. It's rigid. It doesn't bend whatsoever. It's completely stiff. That's quite awkward with fishing though, because really you want your rod to kind of your fishing rod to kind of bend, to be able to go to maybe awkward spots or be able to move about in the water. So that isn't ideal. So being rigid isn't ideal. But fishing rods should be flexible. So being rigid is not sensible, or a sensible assumption to make. Okay, and so there we are. Okay, then it says question 2. A diver dives from a diving board into a swimming pool with a depth of 4.5 meters. The height of the diver is h is 10 take away 0.58 x squared, between 0 and 5 for x. So again, x is a horizontal distance, h is height above water. Then it says for part A, find the height of the diver when x is 2. Okay, so when x is 2, then very simply the height, if I sub 2 in, is 10 take away 0.58 of 2 squared, which would be 7.68 meters. Then part B says find the horizontal distance from the end of the diving board to the point where the diver enters the water. Right? So, what this is kind of saying is, again, it's a quadratic. So the motion of the diver will look like this. So you have water, and then it might go under. But then it's from a plank, right? If you imagine a diver that's on a plank, it starts here and ends, and we want to from the end of the diving board initially, right? That's initially to when the diver enters the water. So the horizontal distance is here. So actually, in turn, we just want to find, well, if the water is the ground level, right? If you will, it's the water level. There's no height. So actually, if we want to find where the diver enters the water, we just set h to 0. So then if we set h to 0, then 0 equals 10. Take away 0.58 x squared. Then we solve for x. So then 0.58 x squared is 10. If we divide by 0.58, we get x squared to be 10 divided by 0.58 to be 500 over 29. So then if we square root that, we get x to be, well, plus or minus 4.15 meters to do decimal places. Plus or minus, because obviously we square root and we'll get two solutions. But obviously here, there has to be a sort of positive, it's distance, right? So it has to be a positive thing. So x has to be positive. And that also makes sense because we're told here x can only be between 0 and 5. So with that in mind, x must be positive, so x can only be positive 4.15 meters. And so there we are. That is the horizontal distance from the diving board to when it enters the water. Okay, here's where the modelling kicks in. So in the model, the diver is modelled as a particle. Describe the effects of the modelling assumption. So, particle means basically firstly the swimmer the swimmer is modelled as a single point. And what that means is, well, it means it's dimensionless, okay? Now maybe you might critique that and think, well, how can a whole human being be just literally an invisible sort of point in space rather than, you know, a human shape with 3 dimensions and all sorts. Anyway, that's a single point. Also, that the swimmer experiences no rotational or air resistive forces. So as the swimmer dives through the air, there's no air resistance opposing it. And also the swimmer doesn't rotate or turn in any way. Okay, it completely dives straight on. Okay, then that's the assumptions of a particle. Then part D, lastly, comment on the validity of the modelling assumptions we just said for the motion as the diver enters the water. So once it enters the water, how valid or sensible would these assumptions be? Well, I mean, well, the thing is, when it's passing through water, when you're in water, it's a whole different ballgame, I guess. When you're swimming in water, that's very different to just diving in the air. Okay, and so, for example, you might anticipate because especially like the waves of the water, right, when you're in the water, you might experience a lot of rotation of water swashing around the waves, even in a swimming pool, right? A lot of waves and stuff that kind of move you around, right? So it has that sort of rotation forces that you would expect. So I'm going to say that motion in underwater is significantly different to in air. Or being airborne. I'll say to being airborne. Or diving, right? So for example, diver may experience a significant rotational force on it, acting on him. Okay. Cool. And obviously as well, once you actually hit the water, you would expect a lot of air resistance as well. Actually, the instant you hit the water, right? And even as you fall through the water, a lot of the air, there might be a lot of air resistance in the water, as obviously you dive in and then you slow down quite massively. Okay. Also stuff like drag as well. You know, there might be other forces like drag in the water which you might not anticipate, again because motion underwater is quite different to being outside water, right? Or other forces like drag. And so there we are. So that is modelling assumptions. Again, I would advise for this particular topic to actually come back at it towards the end of your study. If you're finishing mechanics, this should be a good recap. I would not sit here and memorise it all, just how as it is. But yeah. But that's it for now. I'll see you next time.